For about 400 million years after the Big Bang, the universe was dark. No stars, no galaxies, no light of any kind crossing the void. Just an enormous cooling ocean of hydrogen and helium gas, spreading outward in every direction, nearly perfectly smooth, nearly perfectly uniform, with nothing inside it that you would recognize as structure. That is the universe you came from. And the question of how it got from there to here, from featureless dark to the 100 billion galaxies visible in the deepest images ever taken by human telescopes, is one of the stranger stories in science. Here is why it matters personally. Every atom of calcium in your bones was forged inside a star. The iron in your blood was assembled in a stellar core and scattered by a supernova explosion billions of years before the solar system existed. The oxygen you are breathing right now was processed through multiple generations of massive stars, each one living and dying inside a galaxy, enriching the surrounding gas with heavier and heavier elements over billions of years. Without galaxies, none of that chemistry happens. Without that chemistry, there is no rocky planet, no ocean, no biology. The story of how galaxies formed is, in a very literal sense, the story of how the raw materials of everything you are came to exist. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. So how does a smooth, dark, featureless universe build something like the Milky Way? That is not a simple question. For decades, astronomers assumed the broad outlines were understood. Gas collapsed under gravity, stars formed, galaxies assembled. Clean, sequential, manageable. What the evidence has actually revealed is something far stranger. There is an invisible substance permeating the universe, something that outweighs all the stars and gas and dust by a factor of 5. Something that does not emit light or absorb it, that has never been directly detected in a laboratory, and without which no galaxy would ever have formed at all. The structure of every galaxy you have ever seen in a photograph was built first in the dark by something we cannot see. Then there are the first stars themselves, enormous objects unlike anything burning in the sky today, that lived for only a few million years before destroying themselves and permanently altering the chemistry of the universe. And the collisions, billions of years of galaxies crashing into each other and merging, building larger structures from smaller ones. The Milky Way itself assembled from dozens of smaller galaxies that no longer exist as separate things. And now, images from the James Webb Space Telescope showing galaxies in the early universe that are far too large and far too bright for our best models to explain. Galaxies that, by the numbers, should not be there. What you are about to see is not a settled history. Parts of it are still being figured out. The answer starts before any star ever existed, and it starts in the dark. The Milky Way is roughly 100,000 light-years across. The number that gets used most often to describe it, 200 to 400 billion stars, is an estimate. This was because nobody has ever counted them. Nobody ever will. The best we can do is measure a region, extrapolate. Accept that the uncertainty swallows 100 billion stars without apology. That number is so large it stops being useful almost immediately. So here is a different way into it. If you tried to count every star in the Milky Way at a rate of 1 per second, the count would take longer than the current age of the universe. You would need to have started before the Big Bang, and you still wouldn't be done. But the stars are only part of what a galaxy is. In some ways, not even the most important part. Between the stars there is gas, enormous clouds of hydrogen and helium, some cold and dense, and on the verge of collapsing into new stars. Others hot and diffuse, and still expanding outward from the explosions of stars that died millions of years ago. There is dust, tiny grains of carbon and silicate that scatter light and obscure whole regions of the sky from our view. That dust is not inert. It is the raw material of planets. The silicate in a grain of interstellar dust and the silicate in the rock under your feet are the same substance. Separated by billions of years and a brief stint inside a forming solar system, then there is something you cannot see at all. Around the Milky Way, extending far beyond the visible edge of the galaxy's disk, is a halo of dark matter. It does not emit light. It does not absorb light. It does not interact with anything except through gravity. But it is there, and by mass, it is the dominant component of the galaxy. The stars and gas and dust that produce every photon of light you have ever seen from the night sky account for only a fraction of the Milky Way's total mass. The dark matter halo is several times more massive than all of that visible material combined. It extends roughly 10 times farther out into space than the farthest stars. The galaxy you think you are looking at when you step outside on a clear night is a thin, visible layer wrapped around something much larger and much stranger. How far away is the nearest thing like it? The Andromeda galaxy sits about 2.5 million light-years from here. That light crossing your eye right now left Andromeda when the earliest members of the genus Homo were first appearing on Earth. In between the two galaxies, there is not quite nothing. There are smaller satellite galaxies, streams of stripped stars, thin threads of gas, but the space is close enough to empty that the distance is genuinely hard to hold in mind. 2.5 million light-years is the gap between the two largest members of our immediate neighborhood. The nearest galaxies beyond our local group are tens of millions of light-years away. Pull back farther. The observable universe contains something on the order of 2 trillion galaxies. That estimate has shifted upward significantly as telescopes improved, and it may shift again. 2 trillion. Each one a gravitationally bound system containing billions to hundreds of billions of stars. Its own gas supply, its own dust, its own invisible dark matter halo. Some are larger than the Milky Way by a factor of 10. Some are smaller by a factor of 1,000. Dwarf galaxies exist that contain only a few million stars and barely qualify as galaxies at all by some definitions. Giant elliptical galaxies sit at the centers of galaxy clusters and contain more stars than there are grains of sand on every beach on Earth. The range is extraordinary. Here is where the common picture breaks down. Most people, if asked what a galaxy is, would say something like a big collection of stars spinning in space. That is not wrong exactly, but it leaves out almost everything that matters. A galaxy is not a static object, it is a cycle. Gas collapses into stars. Stars burn for millions or billions of years, fusing lighter elements into heavier ones. Then they die, some quietly, shedding their outer layers into space. Others violently, exploding and scattering material across thousands of light-years. That expelled material mixes back into the surrounding gas, enriched with the heavy elements the star spent its life producing. New generations of stars form from that enriched gas. The cycle runs continuously, and it has been running in the Milky Way for almost 13 billion years. The galaxy is not a collection of objects so much as a process a slow, enormous, ongoing chemical transformation powered by gravity and nuclear fire. That process does not run the same way in every galaxy. Spiral galaxies like the Milky Way have flat rotating disks threaded with lanes of gas and dust, with star formation still actively occurring. Elliptical galaxies are rounder, redder, largely quiet. Their star formation shut off billions of years ago, their gas either consumed or expelled. Irregular galaxies have no organized structure at all, often because a collision or close encounter tore apart whatever order they once had. Dwarf spheroidals are nearly featureless balls of old stars, almost no gas remaining, ghosts of what were once more active systems. These are not just different shapes, they represent different life histories, different relationships between a galaxy and its environment, different outcomes from the same basic, starting material. That last point is the one worth sitting with. Every galaxy visible in any deep field image, from the orderly grand spirals to the shapeless smears of irregular dwarfs, began from the same kind of raw material under the same physical laws. The universe did not start with spirals in one place and ellipticals in another. It started with nearly featureless expanding gas, with only the faintest wrinkles in density to break the uniformity. Everything you see in the night sky, the whole staggering catalogue of galactic shapes, sizes, colors, behaviors, is the result of those wrinkles being amplified by gravity over billions of years. In slightly different ways, in slightly different environments, producing wildly different outcomes. All of that diversity, every shape and size of galaxy visible eye, and the night sky grew from the same featureless early universe. Tracing how it happened is one of the central projects of modern science. In the first 380,000 years after the Big Bang, light couldn't even travel freely through the universe. The entire cosmos was a plasma, a dense, superheated fog of electrons and protons so tightly packed that any photon trying to move through it immediately collided with something and scattered. Think of trying to see through a wall of white-hot steam. The light was there, but it went nowhere. It bounced. It ricocheted. It was trapped inside a universe that had not yet cooled enough to let it escape. Then, at roughly 380,000 years after the beginning, the temperature dropped to around 3,000 degrees. Electrons and protons combined into neutral hydrogen atoms for the first time. The fog cleared, and the light that had been trapped was suddenly free to travel in all directions across the cosmos. We can still detect that light today. It's called the cosmic microwave background, and it is the oldest light in the universe. But here is what happened next. Nothing. For a very long time, almost nothing at all. The universe expanded. It cooled. The hydrogen and helium gas that filled all of space thinned out gradually as the cosmos stretched in every direction. There were no stars producing ultraviolet radiation. There were no galaxies concentrating heat. There was no light source of any kind, anywhere. Astronomers call this period the Cosmic Dark Ages, and the name is not dramatic license. It is a literal description of what the universe was. Dark, silent, expanding. A vast, cooling ocean of gas with no internal illumination and no structure you would recognize. This phase lasted somewhere between 100 and 400 million years, depending on where exactly you draw the line. On a cosmological scale, that is a blink. On any human scale, it is a number too large to sit comfortably in the mind. What was actually in this darkness? Mostly hydrogen, about 75% hydrogen, roughly 25% helium by mass, and trace amounts of lithium. That is almost the complete inventory of matter in the early universe. No carbon, no oxygen, no iron, none of the heavier elements that make up planets or biology or anything we would think of as interesting chemistry. Just the two simplest atoms ever assembled, cooling slowly inside an expanding universe that had no particular interest in putting them together into anything more complicated. Alongside this ordinary gas was something else: dark matter. Enormous quantities of it, spread through space in ways that did not perfectly match the distribution of the hydrogen and helium. It didn't glow. It didn't interact with the gas in any obvious way, but it had gravity, and gravity is patient. Dark matter was already beginning to do the only thing it does. It was pulling. Now here is the question worth sitting with. If the universe was this uniform, this featureless, how did anything ever form at all? A perfectly smooth universe would stay smooth forever. Gravity pulling equally in all directions doesn't build structure. It just holds everything in place. For galaxies to eventually exist, something had to break the symmetry. Something had to create a difference. Some regions slightly denser than others, some regions slightly emptier. And that something happened before any of this. It happened in the first fraction of the first second of existence, at scales so small they make atoms look enormous. Quantum mechanics says that at sufficiently small scales, the universe is fundamentally uncertain. Particle positions, energy levels, density, none of these are perfectly fixed. They fluctuate randomly, constantly, at the tiniest scales. In the first moments after the Big Bang, the entire universe was compressed into a region smaller than any particle we know, and those quantum fluctuations were happening across it. Then inflation occurred, a period of extraordinarily rapid expansion in which the universe ballooned outward by an enormous factor in a tiny fraction of a second. What inflation did to those quantum fluctuations was stretch them. Patterns that existed at subatomic scales were expanded to cosmic proportions. Random quantum noise became real, physical variations in the density of the early universe. Some regions wound up very slightly denser than average. Some regions wound up very slightly emptier, not by much. The differences were minuscule. Those differences showed up in the cosmic microwave background. When the fog cleared at 380,000 years and that ancient light was released, it carried an imprint of the density variations that existed at that moment. Different temperatures in slightly different directions across the sky. The maps we've made of the cosmic microwave background, most recently with the Planck satellite, show this directly. You're looking at a portrait of the infant universe, taken when it was less than 1/400th of 1% of its current age. Every slight warm spot on that map is a region that was, at that moment, very slightly denser than its surroundings. Every slight cool spot is a region that was very slightly emptier. The differences are small enough that they require sensitive instruments to detect at all. But they are real, and they were the only thing the universe needed to get started. Then the Dark Ages settled in, and those variations just sat there, cooling, expanding, waiting. This is the part that's easy to underestimate. Nothing dramatic was happening on human timescales. The universe wasn't building toward anything visible. Gas was cooling. Dark matter was very, very slowly drifting toward the denser regions. The overdense patches were pulling in their neighbors, becoming fractionally denser still. It was a process playing out across hundreds of millions of years without a single photon to show for it. No explosion, no announcement, just gravity, working silently on slightly uneven ground in the dark. What had to happen before anything could ignite? The gas had to cool enough that pressure couldn't support it against gravity. The dark matter had to concentrate enough to create gravitational wells deep enough for ordinary gas to fall into. The density in certain regions had to cross a threshold, a point where collapse became inevitable rather than just possible. None of these conditions were met quickly. The universe had to wait. It had to cool further, expand further, let gravity accumulate its slow advantage. And inside all that waiting, those quantum wrinkles from the first instant of existence were being amplified, slowly, into the architecture of everything that would come next. Those wrinkles were imperceptibly small, a few parts in 100,000, and they were going to build everything. In 1978, an astronomer named Vera Rubin published measurements of how fast stars at different distances from the center of a galaxy were moving, and the numbers made no sense. Here is what the numbers should have shown. When you move away from the center of a galaxy, the amount of visible matter pulling on you drops off. There are fewer stars, less gas, less of everything you can actually see. Basic physics says that the farther out you go, the slower things should be moving. Rubin's measurements broke it completely. The stars at the outer edges of the galaxies she studied were moving just as fast as the stars near the center. In some cases, faster. No slowdown, no drop-off. Just a flat rotation curve stretching out to the edge of the detectable disk, as if there were no edge at all. Other astronomers looked at other galaxies and found the same thing. Whatever was holding those outer stars in their orbits, it was not the visible matter anyone had mapped. There were two possible responses to this finding. One was that our understanding of gravity was wrong at large scales. The other was that there was matter out there we couldn't see. For decades, a small group of physicists pushed on the gravity explanation, developing modifications to Newtonian dynamics that could reproduce some of the observations. But the modifications kept failing in new situations. The invisible matter explanation, uncomfortable as it was, kept working. It worked for rotation curves. It worked for the bending of light around galaxy clusters. It worked for the pattern of temperature fluctuations imprinted on the cosmic microwave background radiation. Every independent line of evidence pointed the same direction. Something was out there, and it was everywhere. Astronomers call it dark matter, which is a slightly misleading name. Dark implies that it absorbs light, or blocks it, the way a dark cloud crosses the sky. Dark matter doesn't do that. It doesn't interact with light at all. It doesn't absorb photons, doesn't reflect them, doesn't emit them. It passes through everything we know of without leaving a trace. The only thing it appears to do is gravity. It has mass. That mass attracts other mass, and apart from that single interaction, it is as close to nothing as something can be while still existing. We know dark matter exists by what it does to the things around it. What it actually is remains genuinely unknown. Now go back further in time. Back to the cosmic dark ages described in the previous section, when the universe was a nearly uniform soup of hydrogen, helium, and these invisible particles drifting through a hot, expanding sea of radiation. In those early conditions, ordinary matter had a problem. It was coupled to the radiation, meaning it was constantly being pushed and pulled by the pressure of light itself. Ordinary gas couldn't simply fall toward denser regions and stay there. The radiation pressure kept pushing it back out. The density fluctuations in ordinary matter, those tiny quantum wrinkles, a few parts in 100,000, were too small, and the radiation pressure fighting against them was too strong. If ordinary matter had been working alone, those fluctuations would have oscillated without growing, and the universe today would be smooth and empty. Dark matter changed everything. Because dark matter doesn't interact with radiation, it didn't have that problem. While ordinary gas was being buffeted back and forth by photon pressure, dark matter was quietly doing what gravity told it to do. It began falling towards slightly denser regions. It began clumping. Slowly, over hundreds of millions of years, those tiny overdensities in the dark matter grew. The clumps attracted more dark matter. The clumps merged with other clumps. The whole time, ordinary matter couldn't follow yet, still pinned in place by radiation pressure. But the dark matter kept building structure anyway, invisible and patient, constructing the scaffolding before the visible universe had any idea what was coming. Then, around 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen. The radiation pressure dropped away almost instantly on a cosmic timescale. Ordinary matter, freed from that constraint for the first time, looked around and found that dark matter had already built enormous gravitational wells across the universe. The gas didn't have to start from scratch. The framework was already there. Think of it like a bowl. The dark matter halo is the bowl, dug deep and waiting, and ordinary gas is sand being poured in from above. The gas follows the contours of the bowl it cannot see. It falls in. It settles. It concentrates. The deeper and larger the dark matter well, the more gas falls in, and the more mass accumulates in one place. What happens next, once enough gas piles up in one of those wells, is the beginning of everything we would eventually recognize as a galaxy. But that step comes next. What matters here is that the bowl had to exist first. The halos that dark matter built were not flat disks. They were roughly spherical, extending far beyond the regions where gas would eventually settle and stars would eventually form. They were enormous. The dark matter halo surrounding a galaxy like the Milky Way extends hundreds of thousands of light years in every direction, dwarfing the visible disk. The stars and spiral arms and glowing nebulae that we can photograph represent a thin concentration at the center of something vastly larger that we cannot photograph at all. When Rubin measured those flat rotation curves, she was measuring the gravitational reach of structures that extend well beyond where any telescope can see. The outer stars weren't moving too fast for the visible galaxy. They were moving at exactly the right speed for the full size of the halo they were embedded in. This is worth sitting with for a moment. Everything you have ever seen in a picture of a galaxy, every spiral arm, every glowing star cluster, every column of dust backlit by young blue stars, is a relatively thin concentration of ordinary matter sitting inside a much larger invisible sphere. It is a bright core inside something much bigger. By mass, the dark matter halo outweighs the stars and gas by a factor of roughly 5-to-1 in a system like the Milky Way. Some halos are even more extreme. The visible parts of a galaxy, the parts we name and photograph and study, are something like a small fire burning at the bottom of a deep, dark well. The well is what makes the fire possible, but you can only see the fire. And here is the harder implication. If this is true for individual galaxies, it is true for the universe as a whole. Ordinary matter, protons, neutrons, electrons, everything that has ever been touched or measured or looked at, makes up roughly 5% of the total mass-energy content of the universe. Dark matter accounts for about 27%. The remainder is something else entirely. The mysterious dark energy driving the universe's accelerating expansion, which is a different problem for a different section. But just the dark matter alone outweighs all the stars and gas and planets and black holes and everything else we have ever detected by more than 5 to 1. The universe we can see is a minority stake in something we cannot. The stars and gas and dust that make up everything we can see in a galaxy, in a very real way, just the visible tip of a much larger invisible structure. Gravity is patient. It does not need to be strong. It does not need to act quickly. It only needs time. And in the early universe, time was the one thing available in extraordinary supply. The density fluctuations left over from the Big Bang were not large. A few parts in 100,000. That is how different the denser regions were from the emptier ones. By any measure that matters to human intuition, the early universe was almost perfectly smooth. But almost is not the same as perfectly, and gravity knows the difference. Here is what happens when you give gravity a slight advantage. A region of space that is fractionally denser than its surroundings has fractionally more gravitational pull. It draws in nearby matter. As it draws in that matter, it becomes denser still. As it becomes denser, its pull increases. The slightly emptier regions around it lose matter to their denser neighbors, becoming emptier still, their gravitational influence weakening. There is no mechanism to stop this. There is no restoring force pushing matter back toward equilibrium. The process runs in one direction only, and it runs indefinitely. What starts as an almost imperceptible wrinkle in the density of the universe, given enough time, becomes a wall of matter, a filament, a collapsing halo. This is not a rapid process by any man's standard, but across hundreds of millions of years, the math is relentless. Dark matter moved first. This is the key fact. Ordinary gas in the early universe was still coupled to radiation. It was being pushed around by the intense pressure of photons, held back from collapsing freely under gravity. Dark matter doesn't interact with light at all. It feels no radiation pressure. While ordinary hydrogen and helium gas was still being buffeted and smoothed out by that photon pressure, dark matter was already quietly clumping, responding to gravity without any competing force to resist it. The density fluctuations that ordinary matter couldn't yet act on, dark matter was already amplifying. It had a head start measured in tens of millions of years, and it used that head start to build the scaffolding before the ordinary matter even knew what was coming. What dark matter built was halos. Roughly spherical concentrations of this invisible mass, growing by pulling in more dark matter from their surroundings, growing by merging with smaller neighboring halos, gradually accumulating mass, the way a snowball accumulates snow rolling downhill. These halos had no sharp edges. There was no surface you could land on. They were simply regions of elevated density in an invisible sea of dark matter, but their gravitational effect was real and growing. Deep inside the densest halos, the gravitational potential was becoming steep. Something falling into that potential well would fall for a long time before it slowed down. Ordinary matter, once it was finally free to move, was going to fall a very long way. When the universe was roughly 380,000 years old, photons and ordinary matter decoupled. Light streamed away in all directions. We see that light today as the cosmic microwave background, and ordinary gas, no longer held smooth by radiation pressure, was suddenly free to respond to gravity. It looked around, so to speak, and found that the dark matter halos had already been waiting. The gas began to fall in. What happens to gas falling into a gravitational well? It accelerates, and as it compresses, it heats up. This is not a subtle effect. Gas falling into a sufficiently deep potential well can heat to millions of degrees. That heating creates pressure, and pressure resists further collapse. So here is the problem. The ordinary matter that falls into a dark matter halo needs to radiate away that heat somehow before it can collapse further and begin forming stars. If the gas can't cool, it just sits there, hot and diffuse, unable to do anything interesting. This is why not every dark matter halo produced a galaxy. A halo had to be massive enough, and the gas inside it had to be able to cool efficiently before anything recognizable as a protogalaxy could form. The cooling is done by atomic physics. Hydrogen atoms, heated by compression, emit photons as electrons drop back to lower energy levels. Those photons carry energy away from the gas. As the gas loses energy, its temperature drops. As its temperature drops, pressure support weakens, and gravity, which has been waiting patiently the whole time, begins pulling the gas inward again. The gas sinks deeper into the dark matter halo, compresses more, heats again, radiates again. Slowly, over millions of years, ordinary matter spirals inward through this cycle until the densest, coolest pockets are sitting deep in the core of the halo, compressed and cold enough that they are finally approaching the conditions needed for something dramatic. The smallest halos went through this process first, simply because they were the first to form. Gravity had amplified the smallest density fluctuations earliest, not because small scales were special, but because small-scale overdensities had a shorter distance to collapse. Those early small halos weren't massive enough to contain enough gas for large-scale star formation, but they were the seeds. Over time, they merged with neighboring halos, and the merged structures pulled in more gas, and the cycle of heating and cooling played out on a larger and larger stage. The structure built itself from the bottom up, each generation of halos feeding into the next, the whole architecture becoming more complex and more massive with every passing 100 million years. By a few 100 million years after the Big Bang, there were places in the universe where ordinary matter had been falling into dark matter wells for long enough that something was about to happen. The first stars were monsters, not in any metaphorical sense. In a purely physical sense, the first stars that ever ignited in the universe were objects so massive they would dwarf anything alive in the sky today. Current estimates place them at somewhere between 100 and 1,000 times the mass of our Sun. Some models push even higher. To understand why they were so extreme, you have to understand what they were made of, and more importantly, what they were not made of. Every star forming today in the galaxy forms inside a cloud of gas that contains traces of carbon, oxygen, silicon, iron, and dozens of other elements heavier than helium. These elements are called metals by astronomers, which is a term that covers everything on the periodic table past hydrogen and helium, whether or not the element is actually metallic. When a gas cloud collapses to form a star today, those heavy elements play a quiet but essential role. They radiate heat away. They act as a cooling agent. allowing the collapsing gas to shed energy and compress further without heating so dramatically that the pressure stops the collapse. Metals make it easier to build small, stable stars. Take the metals out, and the physics changes completely. The first stars had no metals. The gas that collapsed to form them was the gas left over from the Big Bang itself, almost purely hydrogen and helium, with trace amounts of lithium. There was nothing else. There had not been enough time, not a single stellar generation, to produce anything heavier. So when those first gas clouds began falling into dark matter halos and collapsing under their own weight, there was no cooling mechanism to keep temperatures manageable. The clouds could not fragment efficiently the way modern star-forming regions do. Instead of breaking into dozens of smaller pieces, each collapsing into a modest star, the early clouds stayed together. They collapsed as single, enormous masses. The result was stars of staggering size. Think about what a star 1,000 times the mass of our Sun actually means. Our Sun is so large that 1,000,000 Earths could fit inside it. A star 1,000 times more massive would contain, by volume, roughly 10 to the 18th power Earths. The number is meaningless to hold in your head. What matters is what that mass does to the star's interior. Gravity scales with mass, so a more massive star is under crushing internal pressure. To balance that pressure, it has to burn hotter and faster, much faster. A star like our Sun can fuse hydrogen for roughly 10 billion years. A star 10 times more massive than our Sun burns through its fuel in perhaps 20 million years. A star 100 times more massive might last only a few million years. A star near the upper end of what population 3 objects may have reached would have burned through its fuel in perhaps 1,000,000 years or less. 1,000,000 years is fast. On a cosmic timeline where galaxies form over billions of years, 1,000,000 years is nearly instantaneous. These stars lit up, blazed at temperatures and luminosities far beyond anything in the modern universe, and then they were gone. But what happened when they died is the part that changed everything. Stars this massive don't just fade out. They don't quietly cool into white dwarfs the way low-mass stars do. Stars above roughly 8 solar masses end in core collapse, a process where the nuclear fuel runs out. The core falls in on itself in a fraction of a second, and the outer layers rebound in a supernova explosion. Stars at the upper end of the population 3 range may have undergone something even more extreme. A pair instability supernova, where the core becomes so hot that energy begins converting directly into electron-positron pairs rather than supporting the star against gravity, triggering a total collapse followed by a thermonuclear detonation that obliterates the star completely. No remnant, just an explosion so powerful it briefly outshines the galaxy it was born in, if a galaxy even existed around it yet. And in that explosion, for the first time in the history of the universe, heavy elements were flung into space. Carbon, oxygen, nitrogen, neon, iron, silicon. The whole machinery of stellar nucleosynthesis had been running inside these stars for their brief lives, fusing heavier and heavier nuclei in their cores, and the supernova scattered all of it outward into the surrounding gas. The next generation of gas clouds to collapse would form from slightly enriched material. Not very enriched. The earliest population 2 stars that followed still had extremely low metal content, 1/100th or 1,000th of the metal abundance in our Sun. But it was something. The cooling efficiency of those clouds was slightly improved. stars could form at slightly smaller masses. The process had begun. There is something else those first stars did that is just as consequential. They produced extraordinary amounts of ultraviolet radiation. Ultraviolet photons carry enough energy to strip electrons from hydrogen atoms, a process called ionization. In the cosmic dark ages, hydrogen throughout the universe was neutral, meaning every proton had an electron paired with it. Neutral hydrogen is very good at absorbing ultraviolet light, which is part of why the dark ages were dark. But when the first massive stars switched on, they began flooding their surroundings with ultraviolet photons. Bubbles of ionized hydrogen formed around them. The electrons were knocked free. As more stars appeared and more bubbles formed, those bubbles began overlapping and merging, spreading outward through the universe. This process is called reionization. Reionization took hundreds of millions of years to complete. It was not a single event, but a gradual phase transition, the universe going from mostly neutral hydrogen to mostly ionized hydrogen. Were there enough stars forming fast enough to drive it? Was it primarily the ultraviolet output of the first massive stars? Or did the first quasars and active galactic nuclei also contribute? Those questions are still being worked out. What is clear is that the universe we observe today, where light can travel freely between galaxies across billions of light years of nearly transparent intergalactic space, is a universe that was made transparent by the radiation of the first stars. Every atom in your body heavier than helium was produced inside a star. The oxygen you are breathing right now, the carbon in your cells, the iron in your blood, all of it was forged in stellar interiors and scattered by stellar explosions. The specific stars that produced the very first batch of those elements were population 3 objects. Objects that no longer exist anywhere in the observable universe, that lived and died before the Milky Way existed, before the solar system existed, before Earth existed. We have never directly observed one. When those first stars died in supernova explosions, they scattered heavy elements into the surrounding gas, and from that moment on, the universe was chemically different, permanently. The first things astronomers would recognize as galaxies looked almost nothing like what that word calls to mind. Picture what you imagine when someone says galaxy. A sweeping spiral maybe, broad arms trailing outward from a bright core, studded with stars, turning slowly against the dark. That image is so familiar, it has become almost a logo for the universe itself. Now set it aside completely, because the first galaxies bore no resemblance to it whatsoever. They were small, they were chaotic, they had no arms, no organized rotation, no clean structure of any kind. If you could somehow travel back and look at one of these objects directly, you might not even call it a galaxy. You might call it a clump. Here is the scale problem. The Milky Way contains somewhere between 200 and 400 billion solar masses of stars. The earliest galaxies, the ones that formed in the first few 100 million years after the Big Bang, contained perhaps tens of millions of solar masses. Not billions, tens of millions. That is a factor of roughly 10,000 times smaller. Imagine shrinking a city down to the size of a single neighborhood block, and you are still not capturing the difference. These were not infant versions of what we see today. They were something qualitatively different, small, dense, turbulent concentrations of gas and young stars, held together by dark matter halos, just barely massive enough to do the job. and the conditions inside them were nothing like the conditions inside galaxies today. The gas that fell into those early halos was almost entirely hydrogen and helium. No carbon, no oxygen, no iron. Those elements had only just begun to appear, scattered by the first supernova. Without heavy elements, gas cannot cool efficiently. It stays hot. Hot gas resists collapsing into stars. So how did these early galaxies form stars at all? The answer is that gravity doesn't particularly care about resistance. Gravity just keeps pulling. The gas was dense enough, the halos deep enough, and the pressure of gravity eventually won. But the star formation that resulted was messy. There were no smooth, settled disks. There were clumps, bright, compact knots of star formation scattered through turbulent gas, each one blazing with massive young stars burning through their fuel at a furious rate. This is the thing that surprises people when they first encounter it. Star formation rates in these early galaxies were not low because conditions were harsh. In some cases, they were actually quite high. Gas was abundant everywhere. Gravity was actively pulling it together in multiple places at once. The result was not one organized star-forming region, but many disconnected ones, lighting up in different corners of the same small system, with no central authority imposing any order. Were these galaxies forming stars efficiently? Not by any modern definition. Were they forming them anyway, relentlessly, chaotically? Yes. Gravity does not require ideal conditions. It only requires mass. What made these early protogalaxies stranger still was how they related to each other. Today, the Milky Way's nearest major neighbor is the Andromeda galaxy, roughly 2.5 million light-years away. The early universe was far more crowded. Density was higher everywhere. Dark matter halos were forming in close proximity, dragging their gas reservoirs with them, and the proto-galaxies inside those halos were constantly within reach of one another. They weren't isolated islands. They were bumping into neighbors, trading gas, pulling material from each other with tidal forces, merging before either one had fully settled into anything stable. A galaxy would begin to take shape, and before it had organized itself into anything coherent, another clump of similar size would come in and scramble everything. Then both would merge, dump more gas into the combined system, and the cycle would begin again. There was no quiet period, no time for things to settle. The first direct evidence for what these early galaxies looked like came not from a prediction, but from a photograph. In 1995, the Hubble Space Telescope pointed at a tiny patch of sky near the handle of the Big Dipper, a region chosen specifically because it appeared to contain almost nothing, and held that pointing for 10 consecutive days, collecting light from the faintest objects detectable. The result was the Hubble Deep Field. Thousands of galaxies packed into an area of sky roughly 1/30th the diameter of the full moon. Some of those galaxies dated back to 700 or 800 million years after the Big Bang, which sounds like a long time, and is actually, in the context of a 13.8 billion year universe, extremely early. What did they look like? They were small. They were bright relative to their size, blazing with star formation. And they were irregular, strange asymmetric shapes, some appearing as compact knots, some as elongated smears, some as multiple bright clumps tethered together in what was clearly an ongoing merger. Almost none of them had the clean, sweeping appearance of a mature spiral. The universe at that age looked nothing like the universe today. Subsequent deep field observations pushed further back. The Hubble Ultra Deep Field, released in 2004 from observations taken over nearly 12 days of exposure, captured galaxies dating to roughly 700 million years after the Big Bang and hinted at even earlier ones. The pattern held. The earlier you looked, the smaller, brighter, and more chaotic the galaxies appeared. The organized spirals and smooth ellipticals we see in the nearby universe were nowhere in evidence. What existed instead was a collection of building blocks, each one incomplete, many of them in the process of merging with something else. Then came a telescope that could see further still. The James Webb Space Telescope, launched in late 2021, began returning data in 2022 and immediately pushed observations back to within a few hundred million years of the Big Bang itself. What it found there will be covered in full later in this series. But the previews alone were enough to signal that the early universe was even more active, even more populated with early structures than anyone had quite expected. The full story of what James Webb revealed and why it unsettled so many assumptions deserves its own section. For now, hold this image. Not the grand spiral you picture when you hear the word galaxy. Something smaller, something clumpy and violent and unfinished, surrounded by other clumpy, violent, unfinished things, all of them pulling on each other and merging and exploding and pulling together again. The universe in its first billion years was not a collection of island galaxies quietly spinning in the dark. It was a crowded, violent arena of collisions and collapses, and the structures forming inside it were being built and torn apart, almost simultaneously. The universe builds galaxies the way cities grow, not by planning from the top down, but by accumulating, piece by piece, from smaller things that came before. That idea has a name. Astronomers call it hierarchical clustering, and it is the dominant framework for understanding how the structures we see in the night sky actually came to exist. The logic is straightforward once you hear it. Small dark matter halos formed first. Those halos merged with neighboring halos, producing larger ones. The larger halos merged with still larger ones. The gas and protogalaxies trapped inside followed the halos wherever gravity led them. Over billions of years, this bottom-up process of accumulation built the massive, complex galaxies we observe today. No blueprint required, just gravity, time, and an enormous number of small things falling toward each other. This is not speculation in the scientific sense. Decades of computer simulations, running the physics of gravity and gas dynamics forward from the early universe, consistently produce a universe that looks like the one we actually inhabit. The right number of galaxies, roughly the right sizes, arranged in the right large-scale patterns. When researchers strip dark matter out of those simulations, the whole structure collapses. The galaxies don't form on time, don't grow fast enough, don't cluster correctly. Put dark matter back in, and the picture snaps into place. What that tells you is that the hierarchical model isn't just a reasonable guess. It's tracking something real. Here is one of the cleanest pieces of evidence, and it's sitting right outside our own galaxy. The Milky Way is surrounded by dozens of smaller satellite galaxies. The Large Magellanic Cloud, the Small Magellanic Cloud, the Sagittarius Dwarf, the Sculptor Dwarf. There are more than 50 of them, most of them tiny and dim, scattered in a halo around us at distances ranging from tens of thousands to a few 100,000 light years. These are not random neighbors. They are surviving remnants of a process that has been feeding the Milky Way for its entire life. Most of the small galaxies that once surrounded our galaxy have already been absorbed. What we see orbiting us now are the ones that haven't fallen in yet. They're next. But what does a galactic merger actually look like? Because the word collision suggests something violent and instantaneous, and that picture is almost entirely wrong. When two galaxies move toward each other under gravity, the process unfolds over hundreds of millions of years. Stars in both galaxies are spread across such enormous distances from each other that even during a full merger, almost none of them actually hit. The space between stars is so vast that you could pass two entire galaxies through each other, and the stellar collision rate would be effectively zero. If you were living on a planet inside one of those galaxies, you might not even notice the stars changing position much at all, at least not on any timescale a civilization could measure. The gas is a different story entirely. Gas clouds are big, diffuse, and they fill large volumes of space between the stars. When two galaxies make a close pass, those gas clouds slam into each other at hundreds of kilometers per second. The collisions are violent and compressive. Shock waves rip through the gas, compressing it suddenly, triggering a cascade of star formation far more intense than anything happening in a quiet, isolated galaxy. Astronomers call this a starburst, and some merging galaxies produce new stars at rates 10 or 20 times higher than normal. The light output of a starburst galaxy during a major merger can exceed the combined luminosity of billions of individual suns born all at once. At the same time, the gravitational tides are reshaping everything. As two galaxies swing past each other, the differential gravitational pull across their structures stretches material outward into long, sweeping streams. Stars get flung onto new orbits. Gas gets stripped away from the outer regions and pulled into trails that can extend for hundreds of thousands of light years. These tidal tails are among the most spectacular structures in the universe, and they are a direct signature of a merger in progress. Images from the Hubble Space Telescope have captured dozens of them. Pairs of galaxies connected by glowing bridges and streamers of displaced stars. Systems in the middle of a gravitational dance that started millions of years ago and won't resolve for millions more. And here is the counterintuitive part about the timescales. A merger that takes 500 million years to complete sounds slow. In human terms, it is incomprehensibly slow. But in the context of how long the universe has been running, 13.8 billion years, 500 million years, is a relatively brief episode. Galaxies that began interacting a billion years ago may have already merged and settled into something new. The universe is old enough that this process has had time to run through multiple cycles. Small things merged into medium things merged into large things, and in some cases, large things merged into still larger things. The end point of that sequence is sitting in every galaxy cluster in the sky. What determines how the merger turns out? Several things. The mass ratio of the two galaxies involved matters enormously. When a giant galaxy absorbs a tiny dwarf, the smaller system gets disrupted and its stars get scattered into the larger galaxy's halo, barely affecting the big galaxy's structure at all. That kind of minor merger happens frequently and contributes steadily to a galaxy's mass without fundamentally changing its shape. But when two galaxies of comparable mass collide, what astronomers call a major merger, the outcome is far more dramatic. both galaxies get disrupted. The organized rotating disk structure breaks down. Stars that once moved in orderly circular orbits get thrown into chaotic paths. The resulting system often looks nothing like either of its precursors. This is why different merger histories produce such different galaxies. A large galaxy that grew mostly through minor mergers, absorbing small satellites over billions of years while avoiding any comparably sized collision, can maintain its spiral disk structure, as the Milky Way has largely done. A galaxy that experienced one or two major mergers had its disk scrambled and ended up as something rounder and less organized. The diversity of galaxy shapes observable in any deep field image is not random. It is a record of different gravitational histories, written in the arrangement of stars. How many mergers built the Milky Way? Based on current estimates from simulations and from the distribution of stars in the galactic halo, our galaxy has absorbed somewhere between 100 and several hundred smaller galaxies over its lifetime. Most left only faint traces, thin streams of stars, subtle chemical signatures in the halo population, slight asymmetries in the outer disk. A few left marks that are still clearly legible billions of years later. The evidence is in the stars themselves, in their orbits and their chemistry, and increasingly in the data from space telescopes capable of measuring stellar motions with extraordinary precision. Every large galaxy in the universe today is, in some sense, a fossil record of all the smaller structures that fell into it and were absorbed over billions of years. At the center of almost every large galaxy in the universe sits a black hole so massive that the word massive stops meaning anything useful. Start with the Milky Way, because it is the one you know. The black hole at the center of our galaxy is called Sagittarius A star, and it contains roughly 4 million times the mass of the Sun. 4 million suns, compressed into a region smaller than our solar system. That number is almost impossible to hold in your mind, and yet, by the standards of what lives at the centers of other galaxies, Sagittarius A star is small. It is modest. It is, in the context of what astronomers have found elsewhere in the universe, practically ordinary. The black holes sitting at the centers of active galaxies, the ones powering the brightest objects ever detected, contain not millions of solar masses, but billions. Some push past 10 billion. A few outliers appear to exceed 40 billion times the mass of the Sun. These are not variations on the same theme. These are objects in a different category entirely. Here is where the story stops being merely astonishing and starts being genuinely unsettling. When astronomers look at quasars, intensely luminous objects powered by black holes in the act of feeding, they can detect them at enormous distances, which means enormous look-back times, which means they are seeing these objects as they existed in the early universe. And what they find, when they look far enough back, are quasars blazing with the energy of black holes, containing 1 billion or more solar masses within the first billion years after the Big Bang. Some appear even earlier. There is a black hole already carrying over 1 billion solar masses at a time when the universe was only 700 million years old. Stars had only been forming for a few 100 million years before that. The first galaxies were still small, chaotic things, barely a few 100 million solar masses in total. And, inside some of them, somehow, sat black holes already containing 1 billion suns worth of mass. This should be almost impossible. The math, when you run it, does not cooperate. To understand why this is a problem, think about what a black hole needs to grow. It needs to eat. Matter falls toward it, forms a swirling disk of superheated gas, and some portion of that gas crosses the event horizon and is consumed. The rest is blasted away by the enormous energy released in the process. Physicists have worked out a theoretical ceiling on how quickly a black hole can feed, a rate called the Eddington limit, set by the balance between the inward pull of gravity and the outward pressure of radiation produced by the infalling gas. Feed any faster than this limit, and your own energy output pushes your food supply away before it can fall in. The physics is brutal, and the ceiling is real. Starting from a seed black hole of perhaps 100 solar masses, the kind left behind by a massive star, growing to 1 billion solar masses at the Eddington limit would take somewhere between 700 million and 800 million years of continuous, uninterrupted accretion. Were the earliest black holes really doing that? For that long? Without a single interruption? The universe in those early epochs was not a calm place. Mergers were frequent, environments were chaotic, gas supplies were irregular. The idea that any black hole maintained maximum feeding continuously from birth to the point of detection strains credibility. So the question is not just how these objects got so large. The question is how they got so large so fast. 3 serious proposals exist, and none of them has been proven. The first is called direct collapse. In the very early universe, before the gas had been enriched with heavy elements by the first generations of dying stars, enormous clouds of hydrogen and helium could potentially collapse under gravity without fragmenting into stars. Normally, when a gas cloud collapses, it breaks apart into clumps that each become individual stars. But if conditions are right, if the gas is hot enough, if the radiation environment is intense enough to prevent cooling, the whole cloud might collapse directly into a single massive object, bypassing the star formation stage entirely. This direct collapse black hole could be born with a mass of tens of thousands to 100,000 suns. Not 1 billion, but far larger than any stellar remnant. A much bigger starting CD. From there, even conventional feeding rates start to produce the right numbers by the time those early quasars appear. The second proposal involves mergers. If the early universe produced dense clusters of smaller black holes in close proximity to each other, those black holes could merge rapidly, combining mass in a way that sidesteps the feeding limit entirely. Each merger is nearly instantaneous by cosmic standards. Merge enough of them quickly enough, and you can build a very large black hole without the grinding patience of gas accretion. The problem is that this requires an unusual environment, extremely dense concentrations of stellar mass black holes in a region small enough for repeated mergers to occur before the cluster disperses. Whether the early universe actually produced such environments in sufficient numbers to explain all the billion solar mass objects we observe is not yet clear. The third proposal is called super-Eddington accretion. What if the Eddington limit is not actually a hard ceiling? In certain geometries, under certain physical conditions, theoretical models suggest that gas can fall inward faster than the standard limit allows, with the excess radiation trapped inside the infalling material, rather than pushing it back out. The black hole swallows more than the limit should permit. Some simulations support this. Some observations of bright X-ray sources in nearby galaxies hint that it may already be happening. If early black holes regularly exceeded the Eddington limit by a factor of several, the growth problem becomes far less severe. But super-Eddington accretion has never been directly confirmed at the scales that would be required, and whether it could operate steadily enough and long enough to explain billion solar mass objects in the first billion years is a genuinely open question. What makes this more complicated is that these possibilities are not mutually exclusive. The real answer might involve all three, in different proportions, in different environments, at different times. Nature rarely uses one mechanism where several are available. And the James Webb Space Telescope has been making all of this worse in the best possible way. Among the early galaxies JWST has detected, galaxies that already shouldn't be as large as they are, some appear to host central black holes that are disproportionately massive, even relative to their host galaxies. In the modern universe, there is a fairly tight relationship between how massive a galaxy's central black hole is and how massive the galaxy itself is. The black hole is typically a tiny fraction of the total. In some of these very early systems, that ratio looks different. The black holes appear to have grown faster than the galaxies around them, or the galaxies haven't had time to catch up, or something about the early universe allowed black holes to assemble in ways the standard picture doesn't account for. Every observation seems to add complexity rather than remove it. Something built these objects in the time available. Something grew a billion solar masses of collapsed matter in a universe that was barely past its own beginning. How those billion solar mass objects grew so quickly is one of the problems in modern astrophysics that nobody has cleanly solved. The biggest galaxies in the universe are also, in a sense, the most dead. Take a giant elliptical galaxy, one of the enormous featureless blobs of stars that sit at the centers of galaxy clusters. These objects can contain trillions of stars. They outmass the Milky Way by factors of 10 or 20 or more. And yet if you looked at the gas around them, you would find it. The raw material is there. Enormous hot halos of gas surrounding these galaxies, extending millions of light years in every direction, containing enough hydrogen to fuel star formation for billions of years. By any reasonable expectation, these galaxies should be churning out new stars constantly. They are not. They stopped. In most cases, they stopped billions of years ago, and they have been sitting quiet ever since. Meanwhile, smaller galaxies, systems far less massive, far less spectacular, are still actively forming stars right now. The universe's most powerful engines went silent first. That is the paradox, and it demands an explanation. The explanation that has survived the most scrutiny points directly at what you just heard about in the previous section. Supermassive black holes. Not their existence, but their behavior when they eat. When a black hole is actively feeding, it is one of the most energetic things in the universe. Gas falling toward the black hole does not drop straight in. It spirals, compressing, heating, radiating. The material forms an accretion disk that can glow brighter than an entire galaxy's worth of stars combined, and a fraction of that infalling energy does not vanish into the black hole. It escapes. It escapes as radiation, as powerful winds of fast-moving particles blasting outward from the disk, and in some cases as jets, narrow columns of plasma accelerated to near the speed of light, shooting out along the black hole's rotation axis and extending sometimes for millions of light years into the surrounding space. The energy output is almost incomprehensible. A single actively feeding supermassive black hole can inject more energy into its surrounding environment in 1 million years than the Sun will produce across its entire 10 billion year life. Now consider what that energy does to the galaxy around it. The gas that surrounds a massive galaxy is cold enough, in principle, to eventually cool further, fall inward, and form stars. This is how galaxies grow. Gas cools, collapses, fragments into clouds, and those clouds become stellar nurseries. But the jets and winds from an active black hole heat that gas. They pump energy into it continuously. Gas that was slowly cooling and falling inward gets blasted back outward, or heated to temperatures where it simply cannot cool fast enough to collapse. The cooling timescale, which might have been hundreds of millions of years, suddenly stretches to longer than the age of the universe. Star formation stalls. Then it stops. This is what astronomers call AGN feedback. Feedback from the active galactic nucleus, which is a polite technical name for a black hole actively tearing through its surroundings. But here is what makes this more than just a dramatic story about black holes being destructive. The feedback is not random, it is self-regulating. When a black hole feeds aggressively, the energy it releases heats the gas and pushes it away, cutting off the very supply of gas the black hole was eating. The black hole starves itself. The jets quiet down. The winds weaken. With less energy being injected, the surrounding gas starts cooling again. Some of it begins trickling back inward. The black hole starts eating again. The cycle repeats. What you have is a thermostat, a self-regulating feedback loop where the black hole's activity level is constantly adjusting in response to how much gas is available, and the gas availability is constantly adjusting in response to how active the black hole is. The galaxy never gets too far in either direction. Too much star formation triggers more black hole feeding, which suppresses further growth. The system stabilizes, and it stabilizes at a very specific place. The evidence for this picture comes from several directions. One of the most striking pieces is a correlation that nobody expected to find. When astronomers measured the masses of supermassive black holes across many different galaxies and compared them to the masses of the stellar bulges surrounding those black holes, they found a tight relationship. Bigger bulge, bigger black hole, with a ratio that holds across galaxies spanning orders of magnitude in total mass. This is not what you would expect if black holes and galaxies were simply growing independently of each other. The black hole is a tiny fraction of the galaxy's total mass. A black hole of 1 billion solar masses sits inside a galaxy of hundreds of billions. They shouldn't know about each other by rights, but they clearly do. They grew together. Something was regulating both of them simultaneously. Another piece of evidence comes from looking at massive galaxies at high redshift, far enough away that we are seeing them as they appeared billions of years ago when the universe was young. There is a period, roughly 10 to 12 billion years ago, when the most massive galaxies appear to have abruptly stopped forming stars. Before that point, they were among the most productive star-forming systems in the universe. After it, they went quiet. The timing coincides with periods of intense black hole activity in the same systems. The quenching was rapid. In cosmic terms, these galaxies went from vibrant to dormant in what amounts to a few 100 million years. Something with enormous energy turned them off. Nothing else in the physics of galaxy formation produces that kind of sudden, powerful suppression. Nothing except the black hole. The picture that emerges from all of this is not a simple one of black holes dominating their galaxies. It is a picture of mutual regulation. The galaxy feeds gas to the black hole. The black hole responds by heating and dispersing the gas. Both systems end up shaped by the same underlying gas supply, each responding to the other across billions of years of coevolution. Take away the black hole, and the gas would have kept cooling, kept collapsing, kept forming stars. The galaxy would have grown far more massive than it did. The presence of that black hole at the center fundamentally altered the outcome. The black hole at the center of a galaxy is not just a passive passenger. It is one of the main things that decided when the galaxy stopped growing. The spiral galaxy is not as stable as it looks. When you see an image of a spiral galaxy, those sweeping arms, that flat luminous disk, the soft glow of a billion stars arranged in something almost too orderly to believe, it looks permanent. It looks like something that was designed and placed. It wasn't. What you're looking at is a temporary balance, a structure that took billions of years of specific, careful history to produce, and one that can be undone in a single catastrophic collision. The fact that the Milky Way is a spiral is not a coincidence. It is a record. It tells you exactly what kind of life this galaxy has lived. To understand why spirals exist at all, you have to start with a concept called angular momentum. When gas begins falling into a dark matter halo in the early universe, it is never falling perfectly straight down. The gas is coming from slightly different directions, with slightly different velocities, tugged by nearby clumps of matter, jostled by turbulence. All of those tiny sideways motions add up to a net rotation. As the gas falls inward, that rotation speeds up. For the same reason, a figure skater spins faster when she pulls her arms in. Conservation of angular momentum means the gas cannot simply collapse to a central point. It has to go somewhere sideways. And so instead of forming a sphere, the gas settles into a disk. Think of water draining out of a bathtub. It spirals, it ends, it rotates. In a galaxy, the process takes hundreds of millions of years, and the disk never fully drains. But the physics behind the shape is the same idea. Once that rotating disk is established, stars begin forming inside it. The gas cools, fragments, and collapses into stellar nurseries spread across the disk in a wide, flat plane. And at that point, you have something that looks, at least in silhouette, like a spiral galaxy. But you don't have the arms yet. Here is where it gets strange. Spiral arms are not fixed structures. The stars inside a spiral arm are not the same stars from one cycle to the next. They cannot be, because the arm itself rotates around the galaxy at a different speed than the individual stars do. Stars in the outer parts of the disk orbit the galactic center more slowly than stars in the inner parts. If the arms were rigid structures made of fixed stars, they would wind themselves up tighter and tighter over billions of years until the spiral pattern was completely erased. That doesn't happen. What astronomers eventually worked out is that the arms are density waves. Imagine a traffic jam on a highway. The individual cars keep moving through it, slowing down, bunching up, then speeding away on the other side. The jam itself sits in roughly the same place, even as every car inside it is different from one moment to the next. A spiral arm works the same way. It's a region of slightly elevated density, slowly rotating around the galaxy, and as stars and gas clouds pass through it, they slow down, compress, pile up briefly, and then move on. The arm appears bright because that compression is exactly the condition needed to trigger star formation. New, massive, intensely luminous stars ignite inside the arm. They burn fast. They die before they have time to travel far from where they were born. So the arm always glows, always looks full, even though the specific stars lighting it up are constantly changing. This is worth sitting with. The thing that makes a spiral galaxy beautiful, those luminous trailing arms, is not a structure at all. It's a wave. It's a pattern moving through material. The stars you're seeing in those arms were mostly born there recently, and most of them will be dead before the arm has completed another full rotation. For that disk and those arms to survive, the galaxy needs to avoid a specific kind of violence. Minor mergers are fine. When a small dwarf galaxy falls into a larger spiral, it mostly contributes gas and stars to the outer regions of the disk. It can actually thicken the disk slightly, add material to it, stir up star formation in the outer arms. This is not destruction. The Milky Way has been swallowing dwarf galaxies for most of its existence, and it is still unmistakably a spiral. Those minor collisions left scars, a thickened outer disk, streams of stars in the halo, ripples in the structure. But they didn't erase the fundamental organization. A major merger is something different entirely. When two galaxies of comparable size collide, the result is chaos. Tidal forces shred the outer regions of both disks. The orderly orbital structure that took billions of years to establish gets scrambled by the gravitational chaos of two massive objects tearing at each other across hundreds of thousands of light years. The gas clouds collide violently, triggering enormous bursts of star formation that consume most of the available fuel in a relatively short period. After multiple passes and final coalescence, what you're left with is not a disk. It's a tangled mass of stars moving in random, overlapping orbits, with no rotation axis, no plane, no arms. The spiral is gone. What replaces it is something else, which is a story for the next section. What this means is that being a spiral galaxy is, in a specific sense, a survival story. It means the galaxy grew, because growth through minor mergers and gas accretion is how disks build up their mass, but never suffered the kind of head-on encounter that would have ended the disk entirely. The Milky Way has had close calls. The Gaia-Enceladus collision, roughly 10 billion years ago, was significant enough to scramble part of the early disk and leave a thick, puffed-out stellar layer above and below the galactic plane. That event left its mark, but it was not enough to destroy the disk. The thin disk we live in today formed afterward, in the relative quiet that followed, as gas settled back into the rotational plane and resumed forming stars. The spiral persisted. There is something almost improbable about that. Every large spiral you can point to in the night sky is a galaxy that threaded a very specific needle, growing massive enough to be impressive while somehow avoiding the catastrophic major mergers that would have erased it. The ordered, rotating disk of a spiral is the product of a specific kind of history. Enough merging to grow, but not so much that the whole structure got scrambled into something unrecognizable. There is a class of galaxy that contains no spiral arms, no active star formation, no cold gas, just hundreds of billions of old red stars moving in orbits with no particular organization, no disk, no rotation you could measure with any confidence. Just a smooth, featureless blob of ancient starlight, shaped roughly like a football or a sphere, hanging in space like something that has given up. These are elliptical galaxies. And they are, in a very specific sense, what happens when the story of a spiral galaxy ends badly. To understand how you get from a spinning structured disk to a featureless elliptical, you have to watch what happens when two spiral galaxies fall toward each other. Not a quick collision. This plays out over hundreds of millions of years. The first thing that happens on the first close pass is that tidal forces reach across the gap between the two galaxies and begin pulling material free. Stars and gas get drawn out into long, sweeping tails, arcing away from the main bodies into the space between them. You can see this happening right now in real galaxies. The antennae galaxies, two spirals caught in the act of merging, have tidal tails stretching hundreds of thousands of light years in either direction. They look like a pair of insects with their legs tangled together. This is what the first pass does. After that first encounter, the galaxies slow down, turn around, and fall back toward each other. The second approach is worse. The structure that was already compromised on the first pass gets more severely disrupted. Spiral arms blur. The disk begins to lose its coherence. Gas clouds throughout both galaxies are slamming into each other at enormous velocities, and the compression triggers star formation on a massive scale. Millions of new stars ignite across a period that is brief by cosmic standards, a few tens of millions of years, burning through enormous quantities of gas. This is called a starburst, and it is as violent as it sounds. By the third approach, if there even is a third, the two galaxies are already unrecognizable. What were once orderly rotating disks are now a tangled mess of stars in scrambled orbits. The gas that once filled the disks has been either consumed in the starburst or heated and blown outward. And then, slowly, over more hundreds of millions of years, the combined system settles. Stars that were once moving in organized circles around a disk are now moving in every direction, crossing each other's paths in chaotic, overlapping orbits. The whole structure contracts slightly under its own gravity and finds a new equilibrium. A smooth, pressure-supported blob. An elliptical galaxy. What's left behind is a stellar population that is almost entirely old. The starburst consumed most of the cold gas. The merger heated the rest. There is no raw material for a new generation of stars. So the galaxy just sits there, slowly fading, as its most massive stars burn out first, and only the small, long-lived red stars remain. Astronomers call these galaxies red and dead. The name is blunt, but it is accurate. The evidence that massive ellipticals are merger products is not subtle. Nearly all of them contain faint shells and ripples in their outer stellar distributions. Structures that persist for billions of years after a merger event and would not exist in a system that had always been a featureless blob. Many of them contain two or more stellar populations with slightly different ages and chemical compositions, reflecting the fact that they were once separate galaxies with separate histories. Virtually every massive elliptical galaxy also hosts a supermassive black hole, often an enormous one, because major mergers tend to feed black holes as efficiently as they feed star formation. In fact, estimates suggest that nearly all galaxies with masses above a certain threshold have undergone at least one major merger since the universe was half its current age. It is not an exotic event. It is the normal fate of large galaxies in a dense enough environment. Here is the part that gets strange. If major mergers produce ellipticals, and if large galaxies grew through hierarchical clustering, small things falling into larger things across billions of years, then the most massive ellipticals in the universe are, almost by definition, the last things to finish forming. The biggest galaxy in a galaxy cluster is not old in the sense of having been assembled early. It is old in the sense that it has been accumulating for the entire history of the universe. Every collision adds more stars. Every merger contributes another stellar population. These objects, called brightest cluster galaxies, sit at the gravitational centers of enormous galaxy clusters and have grown by absorbing smaller galaxies repeatedly over cosmic history. Some of them contain more than 10 trillion solar masses in stars. That number is almost too large to hold in your head. Our entire Milky Way contains a few 100 billion. These things are 40, 50, 100 times larger. Smaller galaxies that wander too close to the center of a cluster do not survive the encounter intact. Tidal forces strip their outer stars into the surrounding space, and what remains spirals inward and merges with the central giant. This process has been going on for billions of years and is still happening now. Some of the largest ellipticals in the universe are visibly surrounded by the disrupted remnants of smaller galaxies that did not make it out. The most massive galaxies in the universe today are, in almost every case, the final merged products of collisions that played out over billions of years, built last, from the most pieces, in the most violent way. The Milky Way is 13 billion years old, give or take a few 100 million, which means it started forming when the universe was less than 1 billion years old. Most people, when they think about the galaxy they live in, picture the familiar image: a flat spinning disk with graceful spiral arms, a glowing central bulge, a quiet and orderly system. But it is incomplete in a way that turns out to be deeply interesting, because the Milky Way did not arrive at that orderly shape smoothly. It got there through billions of years of collisions, absorptions, and upheaval that astronomers are only now beginning to read in full detail. The oldest parts of the galaxy are not in the disk at all. They are in a structure called the stellar halo, a diffuse, roughly spherical cloud of stars that surrounds the entire disk and extends far above and below it. Halo stars are old. Some of them are nearly as old as the universe itself, with ages pushing past 12 billion years. They contain almost no heavy elements, iron, calcium, oxygen, because they formed before enough stellar generations had lived and died to scatter those elements through the surrounding gas. In the language astronomers use, they are metal poor, and that low metal content is a direct timestamp. These are stars from before the galaxy had any real history to speak of. Their orbits are the other telling thing. Disk stars, like the Sun, move in roughly circular paths, all going the same direction in the same flat plane. Halo stars do not. They follow elongated, tilted, chaotic orbits that take them plunging deep through the disk and out the other side. That orbital chaos is a record of violence. These stars were not born where they are now. They were torn from smaller galaxies that fell into the young Milky Way and were shredded apart. The halo is, in a very real sense, a graveyard of galaxies the Milky Way consumed. Younger than the halo, but still ancient, is the thick disk. This is not a different galaxy or a separate structure. It is an older, puffier version of the disk, sitting above and below the thin disk that the Sun lives in, like a cushion on either side of a table. Thick disk stars formed roughly 10 to 12 billion years ago, during a period when the Milky Way was being actively disrupted by mergers and bombardment from other systems. They contain more heavy elements than the halo stars, because by the time they formed, earlier supernovae had already begun enriching the interstellar gas. But they are not as metal-rich as younger stars, and their orbits are thicker and more disordered than the neat circular paths of stars in the thin disk. The thick disk is a snapshot of the Milky Way in middle adolescence, building up, accumulating material, but still chaotic, still being knocked around. Something happened during the thick disk's formation that stirred the galaxy significantly. Then there is the thin disk. This is where the Sun lives, where most of the galaxy's current star formation is happening, and where the spiral arms are most visible. The thin disk formed later as the Milky Way finally settled into something more stable. For a long time, the standard estimate was that the thin disk began forming roughly 8 to 10 billion years ago. But the key point is that the thin disk represents a calmer epoch. Mergers were less frequent. Gas was settling into orderly rotation. The galaxy was, in the language of the field, quiescent, building steadily rather than violently. Were there still disruptions? Yes. The thin disk carries scars of its own, but the character of this period was different from the thick disk era, and you can see that difference in the stars themselves. They are more metal-rich, more orderly, more circular in their orbits. So you have 3 layers, each one the product of a different phase in the same galaxy's history. The halo tells you about the earliest mergers and the first chaotic assembly. The thick disk tells you about a turbulent middle period of heavy disruption. The thin disk tells you about the long, relatively stable epoch that followed. The Milky Way did not grow uniformly. It accumulated in waves, with different regions forming at different times under different conditions, and then settling on top of each other like geological strata. Reading those layers requires measuring individual stars, their positions, their velocities, the precise mixture of elements inside them. And for most of astronomy's history, the data to do that at large scale simply did not exist. That changed with a spacecraft called Gaia, launched by the European Space Agency in 2013. Gaia's mission was specific and extraordinary: measure the positions and motions of stars across the Milky Way with unprecedented accuracy. Not hundreds of stars, not thousands, nearly 2 billion. For each one, Gaia recorded precise coordinates, proper motions across the sky, and in many cases, radial velocities, how fast the star was moving toward or away from Earth. Combined with data on stellar chemistry from ground-based surveys, this created something that had never existed before: a 3-dimensional kinematic map of a significant fraction of the entire galaxy. The scale of the dataset is almost conceptually unwieldy. 2 billion stars. The number is large enough that the data itself had to be released in stages, with the astronomical community spending years extracting what was hid, then inside it. Before Gaia, the story of the Milky Way was told in broad strokes. The halo formed early, from mergers. The thick disk formed next, during a period of disruption. The thin disk came last, in relative peace. That story was not wrong, but it was rough. The details were missing. Which mergers? When, exactly? How large were the incoming galaxies? How did each event change the galaxy's structure and chemistry? Those questions had answers that were either speculative or absent entirely. After Gaia, specific merger events began to emerge from the data with the kind of clarity that makes the story feel real rather than theoretical. Stars whose orbits made no sense as native Milky Way stars could be grouped together and traced back to specific disrupted systems. Bursts of star formation that had left chemical signatures in the thick disk could be matched to specific disruption events at specific times. The Milky Way's history went from a sketch to something approaching a detailed record. What Gaia found, in short, was that the galaxy's past was messier and more eventful than the smooth narrative suggested. Merger events that had been hypothesized were confirmed and dated. New ones were found. The boundary between the thick disk and the thin disk turned out to be less a clean transition and more a complicated overlap. The halo turned out to contain at least two distinct populations with different origins, distinguishable by their orbital properties and chemical compositions. Every time the data was pushed harder, another layer of complexity appeared. The simple picture of the Milky Way, disk, halo, bulge, dun, kept giving way to something richer and stranger underneath. What Gaia found when it mapped nearly 2 billion of those stars was a history far more violent and surprising than the one that had been assumed. Around 10 billion years ago, a smaller galaxy fell into the Milky Way. Not a dwarf, not a wisp of a satellite. Astronomers call it Gaia-Enceladus, and at the time of impact, it carried roughly 1/4 of the Milky Way's total mass. Put that in perspective. The Milky Way at that point was already billions of stars deep, already had a disk forming, already had a center, and then something 1/4 its size came in. That is not a minor disturbance. That is a collision that would have reshaped everything. The event didn't happen in an instant. Nothing at galactic scales does. The whole process played out over hundreds of millions of years, which sounds long until you realize that is just a fraction of the time that has passed since. First came close passes. Gaia-Enceladus swooped in, felt the Milky Way's gravity pulling at its stars, and swung back out. But each pass bled energy away from its orbit. The two galaxies were circling each other like a slow drain, and the outcome was never in question. With every approach, tidal forces tore more stars loose. Trails of stripped material stretched out behind the intruder. Eventually, the last pass didn't end with a retreat. The two systems fell into each other completely. Here is the remarkable thing. Nobody watched this happen. No telescope pointed at our galaxy 10 billion years ago. Everything we know about Gaia-Enceladus comes from evidence sitting in our sky right now, encoded in the motions of stars we can measure today. The Gaia Space Telescope is the reason any of this became clear. Its mission was precise: measure the positions, velocities, and chemical compositions of nearly 2 billion stars in the Milky Way. When astronomers took that data and began sorting through the halo stars, those ancient stars orbiting far above and below the galactic plane in no particular order, they found something that didn't belong. A large population of stars with orbital properties inconsistent with having formed in our galaxy. Their velocities were wrong. Their orbital shapes were wrong. They were moving on paths that made sense only if they had been captured from somewhere else. And when researchers plotted their orbital energies and angular momenta, those stars didn't scatter randomly. They clustered. The distribution stretched into an elongated shape. Astronomers started calling it the sausage. That name stuck, and the whole event became known formally as the Gaia-Enceladus sausage merger. Those sausage stars are the stripped remnants of a galaxy that was torn apart 10 billion years ago. They've been orbiting inside our galaxy ever since, distinguishable from Milky Way stars only if you know exactly what to look for. The fact that we can still pick them out, still separate their orbits from native stars, is extraordinary. 10 billion years of orbital evolution, and the fingerprints haven't washed out. But Gaia-Enceladus didn't just leave ghost stars behind. It physically changed the Milky Way's structure. Before the collision, our galaxy had a disk, a relatively thin, orderly rotating sheet of stars and gas. When Gaia-Enceladus came through, the gravitational disruption hit that disk like a shockwave. Stars got knocked onto higher, more chaotic orbits. The thin disk didn't collapse, but it got puffed up, thickened. What astronomers now call the thick disk, that older, broader layer of stars sitting above and below the main galactic plane, carries the physical scar of this event. Its stars are older, moving on orbits more inclined than the younger thin disk stars below them. The geometry of the thick disk is a record of a violent encounter. Then the gas arrived. Gaia-Enceladus brought its own reservoir of gas with it, and when the two galaxies merged, that gas slammed into the gas already inside the Milky Way. The collision was not clean. Shockwaves propagated through enormous clouds. Dense regions compressed further, and across the galaxy, gas clouds started collapsing. What followed was one of the most intense bursts of star formation in the Milky Way's history. Researchers examining data from Gaia found a sharp spike in stellar birth rates around 11 billion years ago, right at the moment the merger was happening. That spike didn't appear gradually. It appeared suddenly, and it was enormous. Billions of new stars formed in a relatively short window, all carrying the chemical signature of that particular moment in galactic history. Chemistry is a time capsule. Stars record the composition of the gas they formed from, and that composition changes as each generation of stars lives, dies, and enriches the surrounding medium with heavier elements. The thick disk stars formed during the Gaia-Enceladus burst have iron abundances that jumped sharply. Some studies show a 30-fold increase in iron content across the thick disk era. That's not a gradual drift. That's the signature of massive, rapid star formation and the supernova explosions that followed, each one pumping heavy elements back into the gas before the next generation ignited. The story didn't stop there. The Milky Way, having digested Gaia-Enceladus, settled into a calmer phase. The thin disk grew. The galaxy became, by cosmic standards, relatively quiet. But quiet is relative, and a new intruder eventually appeared. The Sagittarius dwarf galaxy has been falling through the Milky Way's disk repeatedly for the last several billion years. Not merging, not yet, but passing through on a decaying orbit that brings it back around every few 100 million years. Each close pass distorts the disk slightly. Each collision between the Sagittarius gas and Milky Way gas compresses clouds and triggers new star formation. Around 6 billion years ago, a noticeable dip in the Milky Way's star formation rate was followed by a disruption that lines up precisely with one of these Sagittarius passes. The galaxy responded. New stars formed in the disturbance. Sagittarius is still out there, being slowly shredded by tidal forces, leaving a long stream of stars tracing its past orbits around the galaxy. What all of this means is that the Milky Way we live in today is not the galaxy it started as. The thick disk came from a collision. The chemical richness of our stellar neighborhood came from a burst of supernovae triggered by a merger. The subtle distortions in the thin disk carry the mark of a dwarf galaxy that is still in the process of being absorbed. The history is written in the stars themselves, in their orbits, in their compositions, in the way they move through the sky right now. The stars formed in that burst of activity are still here, still orbiting, their chemical compositions carrying a permanent record of the collision that created them. If you could somehow stand outside the observable universe and look back at all the galaxies inside it, you would not see a random scatter of points. What you would see is something stranger. A vast, three-dimensional web stretching across billions of light years, with long threads connecting dense knots and enormous empty regions sitting between them. It looks, if you see the computer renderings, almost biological, like a neuron, like a sponge. Nothing about it looks like what you'd expect from a universe that started as a featureless fog of gas. This structure has a name. Astronomers call it the cosmic web, and mapping it has taken decades of observation. The Sloan Digital Sky Survey mapped the positions of hundreds of millions of galaxies across a significant portion of the observable universe. What came back was not noise. It was the same pattern, over and over, at scale after scale. Long filaments of galaxies, each filament hundreds of millions of light years long. Dense clusters sitting at the points where multiple filaments intersect. And between them, vast voids, regions hundreds of millions of light years across, where almost nothing lives. The universe is not filled evenly with galaxies. Most of the volume of the universe is nearly empty. The filaments are not coincidences. They are the direct descendants of the same density fluctuations that built individual galaxies, just operating on a far larger scale. Wherever space was slightly denser than average in the first moments after the Big Bang, gravity got to work. Over time, slightly overdense regions pulled in more matter, while underdense regions gave it up. On the scale of galaxy formation, this process created dark matter halos. On scales 1,000 times larger, the same process carved the cosmic web. The overdense regions became filaments and clusters. The underdense regions became voids. Same physics, same starting conditions, completely different scales. The dark matter did the heavy lifting here too. Because dark matter doesn't interact with light, it wasn't slowed down by radiation pressure the way ordinary gas was. It began clustering first, laying down the scaffolding. Ordinary matter followed, falling along the dark matter structure, flowing like water along channels that were already there. The filaments you see in galaxy surveys today trace, almost perfectly, the structure of the underlying dark matter web. You can't see the dark matter directly, but you can see where the galaxies went, and that tells you where the dark matter must be. So the web emerged. But what happened to the galaxies inside it? Here is something that took astronomers a long time to appreciate. Where a galaxy lives matters enormously for what it becomes. Two galaxies that started out nearly identical can end up completely different depending on whether they fell into a dense cluster or drifted into a void. The environment reshapes them, sometimes violently. In galaxy clusters, the environment is brutal. Clusters contain hundreds or thousands of galaxies crammed into a region a few million light years across, all orbiting inside a bath of superheated gas that fills the space between them. That gas reaches temperatures of tens of millions of degrees. When a galaxy falls through a cluster at high speed, The hot gas strips away the galaxy's own cold gas supply, like peeling the skin from a piece of fruit. The process is called ram pressure stripping, and it is efficient. Once a galaxy loses its cold gas, it can't form new stars. It just keeps the ones it has, which age and dim and redden over billions of years. Cluster galaxies stop forming stars early. They are overwhelmingly red and old and quiet. Galaxies along the filaments have a different story. They receive a more gradual flow of gas from the surrounding cosmic web, feeding star formation at moderate rates over long timescales. They are often spirals, still blue, still building new generations of stars. The Milky Way sits in a relatively modest environment, not a dense cluster, not a void. A small group of galaxies, loosely bound, on a filament connecting larger structures. That modest environment is part of why the Milky Way is still forming stars today. Galaxies in the voids are almost untouched. They evolved slowly, in isolation, receiving little of the disruption that cluster and filament galaxies experienced. They tend to be smaller, bluer, less chemically enriched. They are, in some ways, closer to what the early universe looked like, because they've been left alone to grow quietly, without the violent mergers that built the big galaxies in denser regions. Environment, it turns out, is one of the most powerful predictors of what a galaxy looks like. More powerful, in some cases, than the galaxy's initial mass or composition. Ask where a galaxy lives, and you have already answered a lot of questions about what it is. What makes the cosmic web remarkable is not just that it exists, but that we predicted it before we fully mapped it. Decades ago, cosmologists ran computer simulations of a universe starting from nearly uniform initial conditions, letting gravity evolve the density fluctuations forward in time. The simulations produced a cosmic web. Then the surveys went out and mapped the real universe. The match was striking, not perfect. There are tensions, discrepancies being actively investigated. But the broad architecture was there, exactly where the models said it would be. The pattern of galaxies across the universe is, in a very direct sense, a map of what the universe looked like in its first fraction of a second, amplified by gravity across 13 billion years. The James Webb Space Telescope was not supposed to overturn our understanding of how the early universe worked. It was supposed to confirm it. The plan was straightforward. Build a telescope powerful enough to see the first galaxies directly. Watch them appear on schedule, small and faint and primitive, just as the models predicted. Decades of cosmological simulations had produced a clear picture. The early universe should be filled with tiny, irregular protogalaxies, clumpy and chaotic, slowly building toward the structured systems we see today. Nobody expected a crisis. Nobody was braced for what actually came back. JWST launched in December of 2021 and began returning science data in the summer of 2022. Within months, the first results were already strange. Astronomers started flagging objects in the early data, galaxies sitting at extraordinary distances, seen as they existed when the universe was only a few 100 million years old. That part was expected. The age was not the problem. The problem was what those galaxies looked like. They were massive, not small and faint and embryonic. Massive. Some of them appeared to contain hundreds of billions of solar masses worth of stars, assembled and organized, burning brightly, at a time when nothing that size should have had any chance to exist. To understand why this is a problem, you need to understand what the models were actually saying. The hierarchical clustering model, the dominant framework for galaxy formation for decades, makes a specific prediction about the early universe. Small things form first. Large things come later, assembled from the smaller things through mergers and accretion across billions of years. A galaxy containing several 100 billion solar masses of stars is not a small thing. Under the standard model, building an object like that takes time. It takes many mergers, each one playing out over hundreds of millions of years. It takes dark matter halos growing large enough to hold onto gas, and that gas cooling enough to collapse, and those collapses producing stars, generation after generation, accumulating mass across long stretches of cosmic history. You do not get something that large in a few 100 million years. The math doesn't work, or rather, it didn't. What JWST was seeing were galaxies that appeared to have skipped the line. Objects with stellar masses that, according to every simulation run before 2022, should not have existed until the universe was several billion years old, were sitting there in the data, bright and fully formed, at redshifts corresponding to a universe barely 500 million years old. Some researchers, when they first ran the numbers, assumed they had made an error. They checked the photometry, they checked the redshift estimates, they checked the calibrations. The galaxies were real, the masses were real, and nothing in the standard playbook explained them. Here is how large the discrepancy was. Cosmological simulations of the early universe, the same simulations that had successfully predicted the cosmic web, the large-scale distribution of galaxies across space, the statistics of galaxy clustering, predicted a specific number for how much stellar mass should exist in the universe at very high redshift. When researchers compared those predictions to the JWST observations, some of the detected galaxies appeared to exceed the total stellar mass budget the simulations allowed for their entire observable region, not just above the predicted average, in some cases, above the theoretical ceiling. That is not a small discrepancy you paper over with a correction factor. That is a model telling you something has gone wrong at a fundamental level. Several explanations were put forward immediately. The most conservative was measurement error. Estimating stellar masses from photometric data at extreme redshift involves assumptions about stellar populations, dust content, and star formation history, and those assumptions can compound. Some of the most extreme mass estimates may have been inflated by contamination from active galactic nuclei, black holes pumping out radiation that mimics a stellar signal. Spectroscopic follow-up observations, which give much more reliable data, have confirmed that some early candidates were overestimated, but not all of them. The problem did not go away when the conservative corrections were applied. A significant number of genuinely anomalous galaxies remained. The more interesting explanations involve the physics itself. One possibility is that star formation efficiency in the early universe was dramatically higher than the models assumed. In present-day galaxies, only a small fraction of available gas actually collapses into stars. Feedback from supernovae and black holes blows the rest away. But what if, in the early universe, before that feedback had time to establish itself, the conversion of gas into stars was almost ruthlessly efficient? If even a modest increase in early star formation efficiency is applied to the models, the mass problem becomes significantly less severe. It doesn't fully disappear, but the gap narrows considerably. Another possibility involves the initial density fluctuations themselves. The models assume a specific statistical distribution of those fluctuations, a distribution calibrated against measurements of the cosmic microwave background. But what if that distribution had a longer tail than expected? What if some regions of the early universe were significantly overdense relative to the average, producing halos massive enough to host unexpectedly large galaxies much earlier than the standard distribution would allow? This would not require changing the physics of galaxy formation at all. It would just mean the early universe was slightly lumpier than the best current measurements suggest. A more radical proposal involves dark matter. The standard model uses cold dark matter, meaning dark matter particles that were moving slowly when structure began forming, which allows small-scale clumping to proceed freely. Some researchers have asked whether a different form of dark matter, one with slightly different properties at small scales, might allow halos to grow faster in the early universe, seeding the massive early galaxies JWST is finding. This is speculative. There is no direct evidence for non-standard dark matter behavior. But the JWST results are, for the first time, putting real observational pressure on the cold dark matter assumption. What nobody is seriously arguing is that JWST made the wrong observations. The instruments work. The data is real. And the honest answer to the question of what is causing this is that the field does not have a clean consensus yet. Papers are being published every month. Simulations are being revised. Old assumptions are being tested against new data in ways that would have been impossible 3 years ago. Some of the most respected cosmologists alive are publicly saying that the early universe is more complicated than they thought. That is not a comfortable thing to say after decades of successful predictions. But it is the accurate thing to say. What makes this genuinely exciting, not just unsettling, is what it implies about how much is still left to understand. The models that JWST is straining were not naive guesses. They were sophisticated, well-tested frameworks built on decades of observations. And a single telescope, in its first year of operation, found objects that those frameworks struggle to explain. Whatever the explanation turns out to be, the picture of early galaxy formation that was taught in textbooks as recently as 2021 has been quietly abandoned. The iron in your blood was made in a star that exploded before the solar system existed. Not metaphorically, not approximately. The actual iron atoms circulating through your body right now were forged in the collapsing core of a massive star, ejected in a supernova explosion, scattered across interstellar space, and eventually swept up into the cloud of gas that became the Sun, the Earth, and everything on it. That is not a poetic framing. That is the literal chain of events. And it only happened because galaxies spent billions of years building the conditions that made it possible. The universe started with almost none of this. After the Big Bang, the only elements in existence were hydrogen, helium, and trace amounts of lithium. That is it. No carbon, no oxygen, no iron, no calcium, no silicon. The entire periodic table beyond those first few entries was missing because nothing had been built yet. The first generation of stars, those enormous, short-lived monsters made entirely of hydrogen and helium, were the first factories. They fused lighter elements into heavier ones in their cores, and when they died in supernova explosions, they scattered those elements into the surrounding gas. Carbon, oxygen, neon, magnesium, the universe's chemical inventory expanded in a single violent event, repeated millions of times across millions of early galaxies. That process never stopped. Each generation of stars inherited the chemical leftovers of the generation before it, added more complexity, and passed it forward. The gas that collapsed to form the second generation of stars already contained trace amounts of carbon and oxygen. That gas cooled more efficiently than the pure hydrogen clouds of the first generation, which allowed smaller, longer-lived stars to form. Those stars lived longer, enriched the gas more slowly and steadily, and died in their own explosions. Then came a third generation, and a fourth, each one building on the last. Astronomers call this chemical enrichment, and it is one of the most powerful tools available for reading the history of a galaxy, because the chemical composition of a star is essentially a timestamp. This is where the Milky Way's history becomes readable in a specific and striking way. The oldest stars in the galaxy are found in the stellar halo, those metal-poor stars on chaotic looping orbits that formed in the earliest and most violent phase of assembly. Their iron abundances are extremely low, sometimes hundreds of times lower than the Sun's. They are relics of a time when the galaxy was young, when few supernovae had yet occurred, and when the interstellar gas was still nearly as pristine as the universe had left it. When you measure the iron content of a halo star and find it sitting at a fraction of a percent of the Sun's value, you are looking at something that formed close to the beginning. The thick disk stars are younger. They formed during the turbulent middle period of the Milky Way's history, when mergers were still frequent and star formation was running at a high rate. Their iron abundances are higher, and here the data carries a very specific signature. Around the time of the Gaia-Enceladus collision, roughly 10 to 11 billion years ago, something interesting happened to the chemical record. The merger dumped an enormous quantity of gas into the Milky Way. That gas triggered a burst of star formation intense enough to show up in the abundance measurements of stars that formed at that time. The iron content climbed steeply. Thick disk stars at the end of that era are dramatically more metal-rich than the ones at the beginning. The collision is written into the chemistry as clearly as a layer in geological rock. The thin disk stars, including the Sun, formed later still, from gas that had been enriched by all of that history. The Sun is a relatively metal-rich star for its age, which is part of why the solar system ended up with enough heavy elements to build rocky planets at all. Rocky planets are essentially compressed piles of silicon, iron, magnesium, and oxygen, none of which existed before stellar nucleosynthesis produced them. Without billions of years of supernovae and galactic chemical enrichment, there is no material available to build a planet like Earth. You cannot form a terrestrial world from hydrogen and helium alone. Were the conditions for life always going to emerge from this process? That question is harder, but the chemistry of it is clear. Carbon chains, nitrogen bonds, phosphorus, sulfur. The molecular building blocks of biology require elements that only stars produce. The first generation of stars could not have built a habitable planet around them even in principle. The raw materials weren't there. By the time a star like the Sun formed, those materials had been accumulating for nearly 9 billion years. That gap is not incidental. It is the minimum amount of time the universe needed to produce the right chemistry. This is why the chemical history of galaxies is not a footnote to the story of galaxy formation. It is the part of the story that connects directly to whether anything interesting could ever happen in the universe. Galaxy formation built the furnaces. Star formation lit them. Supernovae distributed the output. And then gravity swept it all back together into new clouds, new stars, new planets. Every cycle enriched the raw material a little more, nudging the universe incrementally toward a state where complex chemistry was possible. The oldest stars in the Milky Way's halo are still there, still orbiting, still carrying in their spectra the record of a time before any of this had happened. The Sun carries its own record, and the planets that formed around it carry the record of everything that came before them. Galaxy formation is not an abstract cosmological process. It is the mechanism that built the raw materials of everything, and the billions of years it took were not wasted. The Milky Way is going to be destroyed, not by a rogue star, not by some catastrophic failure of physics, not by anything that could have been prevented. The Milky Way is going to be destroyed the same way countless galaxies before it were destroyed, by another galaxy falling into it. Right now, 2.5 million light-years away, the Andromeda galaxy is closing in. It is already on its way. The two galaxies are approaching each other at roughly 110 kilometers per second, and in about 4 to 5 billion years, they will meet. What happens after that is not a mystery. We have watched it happen to other galaxies across the universe hundreds of times. We know the sequence. We can run the simulations. The outcome is not in doubt. What is worth sitting with is what that outcome actually means for a galaxy that has been building itself for 13 billion years. Start with what the sky would look like, assuming anything is alive on any planet to see it. Right now, Andromeda is visible to the naked eye as a faint smudge in the constellation of Perseus, a pale thumbprint in the darkness. For the next several billion years, not much changes. Then, gradually, that smudge begins to resolve. It grows. It brightens. The outer spiral arms of Andromeda start to become visible as something distinct from the background stars, a second structure rising in the night sky alongside the band of the Milky Way itself. There would be no single dramatic moment when things started going wrong. The change would be slow beyond any human experience of slowness, stretching across millions of years. But on astronomical timescales, what comes next is sudden. The first close pass would transform the sky entirely. Andromeda's disk begins to distort as tidal forces pull at it. Our own galaxy distorts in response. Long tails of stars, pulled free from both galaxies by the mutual gravitational stress, arc out into intergalactic space. From any surviving planet, the sky would now be occupied by a structure unlike anything the galaxy had contained for billions of years. Two interacting systems, both deformed, both shedding material, the whole scene lit up by furious new star formation, triggered by colliding gas clouds. When the gas clouds of two galaxies slam together at high speed, the compression is violent enough to collapse enormous quantities of material almost simultaneously. Stars ignite by the millions. The rate of star formation during this phase could be 10 or 20 times higher than anything the Milky Way experiences today. The sky would be bright with it. Then the two galaxies would separate again. This is the part that surprises people. A galactic merger is not a single collision. The two galaxies swing past each other, pulled back by gravity, swing past again, each pass slower than the last. The process repeats across hundreds of millions of years. 3 passes, sometimes 4. Each time, both galaxies lose more of their original structure. Each time, the gas supply for new star formation depletes a little further. Each time, the violence of the encounter heats more of the remaining gas to temperatures where it cannot cool and collapse. Eventually, the two systems do not separate again. They coalesce into a single merged object. Here is something worth understanding about that merger. Almost no stars will actually collide. The distances between individual stars are so vast that 2 entire galaxies can pass through each other with virtually no direct stellar impacts. Our Sun is roughly 1.4 million kilometers wide. The nearest star to the Sun is about 40 trillion kilometers away. In a galaxy where that kind of spacing is typical, the odds of any 2 stars hitting each other are negligibly small. What changes for individual stars is not survival, but position. Gravitational perturbations during the encounter can fling stars to entirely different orbits. A star that spent its entire life in the quiet outer disk could end up on a chaotic orbit that carries it thousands of light years out of the galactic plane and back. The Sun's orbit could be fundamentally altered. Whatever planetary system the Sun still has at that point, and it will still have one, since planetary disruption from a galactic merger is not particularly likely, could find itself in a radically different position within the merged galaxy. The end product of all of this has been given a name. Some astronomers call it Milkomeda. Others say Milkdromeda. Whatever you call it, it will not look much like either of its parent galaxies. The organized rotating disk of the Milky Way, the spiral arms, the flat geometry that took billions of years to build, all of it will be scrambled into something rounder and less ordered. Stars that once moved in calm circular orbits will move in elongated tilted paths with no common direction. No cold gas will remain to feed new generations of stars. The result will be a large elliptical galaxy, old and red and quiet, its star formation finished. Everything described in the previous sections of this story, the dark matter halo that seeded the Milky Way's formation, the Gaia-Enceladus collision that built the thick disk, the Sagittarius dwarf galaxy spiraling in across billions of years, all of it will have produced, in the end, raw material for a merger that turns the whole structure into something fundamentally different. This is not a tragedy in any cosmic sense. It is the process. Every large elliptical galaxy in the universe arrived at its current state through exactly this sequence of events. 2 disk galaxies, a slow approach, a violent encounter, a merger, and then silence. The same thing has happened billions of times at every scale across the history of the universe. What makes this one different is only that it is ours, and that the evidence for it is already sitting 2.5 million light-years away, closing in at 110 kilometers per second, unremarkable against the sky. The collision with Andromeda is not an ending specific to our galaxy. It is exactly the same story that has played out for billions of galaxies throughout cosmic history. And in that sense, the Milky Way is simply arriving, a few billion years late, at the same destination. Step back from all of it. The dark matter halos, the merging spirals, the billion solar mass black holes that appeared too early. And what you are left with is a universe that built itself. No blueprint, no single moment when galaxies switched on and the job was done. Just gravity, time, and a set of initial conditions so close to uniform that the differences between dense regions and empty ones were smaller than anything you could measure with a ruler, and from that, everything. The process took 13.8 billion years, and it is still running. That is the part that does not get enough attention. Galaxy formation is not something that happened and then stopped, the way the Big Bang happened and stopped. Galaxies are merging right now. Stars are forming right now inside dark matter halos that have been pulling in gas for billions of years. The Sagittarius dwarf is being shredded by the Milky Way's gravity at this moment. Andromeda is already on its way. The universe is mid-sentence, not at a period. Direct observation confirms this continuity. When astronomers look at the nearby universe, they see mergers at every stage of completion. Some systems locked in the final approach, others recently combined but still settling into equilibrium, their dynamics still actively evolving. The timescale for these collisions spans hundreds of millions of years. A merger that began before dinosaurs walked the Earth might not be finished today. This is not ancient history. It is the ongoing state of the cosmos, visible in real time to those who know where to look. What the science actually shows is a process that was violent, inefficient, and deeply strange at every stage. The first structures collapsed because dark matter, something we still cannot identify, fell into clumps before ordinary gas could. The first stars were probably so massive they lived only a few million years. The first galaxies looked nothing like galaxies, and then things collided, again and again. Small halos merged into larger ones. Protogalaxies cannibalized their neighbors. Gas fell in, triggered star formation, got heated by supernovae and black holes, and got expelled. Then fell back in. The Milky Way alone has absorbed dozens of smaller systems. Every large galaxy in the sky carries the same record of accumulated wreckage. Here is the thing that should stop you. Every atom that makes up the ground you are standing on was processed through at least one stellar interior before the solar system formed. The carbon, the oxygen, the iron, forged in cores, scattered by explosions, recycled through generations of stars across billions of years inside a galaxy that was itself being assembled by collisions. You are not just observing galaxy formation from the outside. You are a downstream product of it. The planet exists because the Milky Way existed. The Milky Way exists because a universe full of dark matter and quantum fluctuations had 13 billion years to work. And yet the picture is not finished. That is genuinely true, not as a disclaimer, but as a scientific fact. The early galaxies that JWST found, massive, bright, present far too soon, do not fit the models that had successfully described everything else. Something about how star formation worked in the early universe, or how dark matter clustered, or how black holes seeded themselves, is not right in our current framework. The question of what dark matter actually is remains completely open. The mechanism that let billion solar mass black holes assemble within the first billion years has no clean answer. These are not minor loose ends. They are load-bearing mysteries sitting at the center of the whole story. That is what makes this worth paying attention to. Not just the scale of it, though the scale is staggering. It is that the universe left evidence everywhere. In the orbits of stars, in the chemical composition of ancient halo populations, in the shapes of galaxies, in the cosmic microwave background. Every observation is a clue, and right now, some of those clues are pointing somewhere the models did not predict. The universe has been assembling galaxies for 13 billion years, and it has not finished yet.